Today we're going to talk about all things climate change mitigation. We're going to look at some of the models that we use to reason pathways for decarbonising, and then we're going to look at a much simpler framework that gets all of you guys involved in producing our own collective decarbonisation pathway. So a bit about me, I'm Dr. Nathan Johnson. I'm a researcher in energy and climate change at CEP, and I've been at the department since 2017, when I was sat in your seats. I'm an alumnus of the energy policy option of the MSc, which I started back in 2017. Since then, I did my PhD and have continued as a postdoc, so I am slowly but surely becoming part of the furniture here. So on with the agenda. So firstly, we're going to look at the relationship between carbon dioxide emissions and climate change. I'm not going to labour this point. You're all MSc environmental technology students. I'm sure you're fully aware of this relationship and its implications, but I think it's important to at least cover this briefly for some context. We're then going to look at some different decarbonisation pathways and the models that we use to derive these pathways. We're also going to consider some of the limitations of those models, and then I'm going to introduce a different framework, a framework that I've dedicated the last 5 or 6 years of my life to refining, improving, and putting out there. And so finally, we're going to build our own pathway based upon this framework. And so the session is going to get quite interactive. So if you haven't already, could you all navigate to menti.com and join the survey using that code on the screen? Okay, so let's start at the top. So what drives global warming? Well, this chart on screen is the crux of the problem. On the y-axis, we have global temperatures, or rather global warming relative to the pre-industrial period. And on the x-axis, we have cumulative CO2 emissions over that same time period. As cumulative emissions have increased, so too has warming. For each trillion tons of CO2 that we put out into the atmosphere, global temperatures rise by roughly ½ a degree. And so this chart comes from the IPCC's 6th assessment report, published back in 2021. And at that point, we had put roughly 2.2 trillion tons of CO2 into the atmosphere, and temperatures had warmed by around 1.1 degrees. You'll notice that the relationship is near linear, which lends itself very well to extrapolation. So here I'm showing 5 different pathways that encompass different levels of future emissions. On the left-hand side, highlighted in blue, you have low emissions scenarios. So between today and 2050, these put out less emissions than the scenarios on the right, the red scenarios. And what does this mean? Well, obviously, the less CO2 we put into the atmosphere, the less the planet warms. And so we need to move from the red pathways, which we were once expected to follow, towards the blue ones. Simple. And it matters not where CO2 is emitted, be it in London or in Lagos, the CO2 will mix within the atmosphere and cause the same impacts the world over. It also matters not what annual emissions are per se, it's the total stock of CO2 that sits within our atmosphere that determines the atmospheric concentration of CO2 and thus warming. So higher temperatures obviously increase climate-related impacts. So here, another chart taken from the IPCC is showing those same pathways but extrapolated not to 2050 but out to 2100, and also showing the temperature implications of those pathways. And so we see that the more we emit, the higher the temperatures become. Now, what does this mean in terms of climate impacts? Well, this chart is showing the relative climate risks and impacts. It's showing the frequency and severity of different impacts, both of which increase as we increase global temperatures. And so it's a little bit complicated, but let's break it down. So we've got the bars relating to the temperatures over on the left, and so yeah, the higher emission scenarios fall well and truly into the darker red section of the bar where the risks and impacts are higher. So let's look at where we're at today, about 1.2, 1.25 degrees of warming now in 2025. Well, if we read across on the graph, you can see that unique and threatened ecosystems are already dealing with quite severe climate impacts. So unique and threatened ecosystems, we can look to coral reefs, which are being bleached at an astonishing rate, and of course the impact of that is that they can no longer support marine life. If we look to a human system, we have small island-dependent states that are shrinking year by year as sea levels rise. We also see that extreme weather events are becoming more frequent and more severe, and the science that attributes extreme weather events to CO2 emissions and warming is growing stronger and stronger, and the evidence base too. And so we need only look at the record-breaking storm seasons we've had across the world over the past decade. The record-breaking wildfires we've seen not only in Australia, the US, but also across Europe. As temperatures increase further, these impacts become wider. They go from small geographical pockets to affecting the entire world. And so they grow. The distribution of these impacts grows until you've got these globally aggregate impacts. And fundamentally, climate change is characterized by tipping points, points at which you have irreversible change within the system triggered by a breach of a threshold, a tipping point. Examples of this are the Atlantic meridional overturning circulation that regulates the temperatures in the Atlantic. If this were to stop and collapse, well, we'd see almost counterintuitively freezing cold temperatures across Europe. Similarly, if we melt the permafrost in Siberia, then we see a rapid release of methane, a very potent greenhouse gas, which triggers further warming, further melting, and you've got this very dangerous negative feedback loop. And so, yeah, climate impacts are becoming more frequent, more severe. I often get asked, climate change is happening, so what? And to my friends, I say, have you not read the news? Because these events are plastered all over the newspapers. So I don't want to dwell on the doom and gloom for too long, but first of all, we'll go to a poll. And so, so firstly, I will ask you, what level of warming is socially acceptable? What level of warming do you feel society should be prepared to accept? And what we end up building is a histogram of responses. This one, we've got many people believe that we should be limiting warming to below 1.5 degrees, some to below 2 degrees. Others are willing to accept much higher levels of warming. Those who are willing to accept the higher levels of warming, may I refer you to the previous slide on climate-related impacts. Over 3 degrees of warming will threaten many Earth and human systems. But yeah, I think generally we see that responses are trending towards that 1.5 and below 2 degrees mark. I think we'll move on. From that slide. Okay, so the next thing to know is that the climate problem is huge. And so this line here, squiggly line, is showing us global net greenhouse gas emissions from 1990 up until roughly the present day. And so we see that emissions have increased at a roughly steady rate over the last 50 years. And to date, we've had about 1.25 degrees of warming, although in individual years, we've seen over 1.5 degrees of warming. This is a decadal average temperature. And so if we were to continue without regard for the climate, without climate policy, we'd be expected to follow this trajectory, the no policy scenario in which emissions continue to increase at roughly historical rates. Warming would exceed 2 degrees by 2050, and by the end of the century, we'd be looking at nearly 4 degrees of warming. disastrous. Fortunately, that is not the trajectory we're expecting to head along. There is no country in the world that doesn't have a climate policy today, and they are enacting and committing to many more going forward. So when we account for all of these different policies that have already been stated or enacted, we bend the curve down to this current policies scenario, where we see that warming is limited to below 2 degrees out to 2050, but by the end of the century, we still see 2.5 degrees of warming. Where we really need to get down to is this decarbonisation scenario, which keeps 1.5 degrees within reach. Rather than a steady flatlining of emissions, we need radical emissions cuts between now and mid-century. That's not enough to keep temperatures below 1.5 degrees. Over the following half-century out to 2100, we would need to draw carbon down from the atmosphere in order to get temperatures to fall back below 1.5 degrees. So it's a monumental task, and no single technology can solve the problem on its own. No matter how widely we deployed wind power or solar power, there is no way of filling that emissions gap with one technology. There is no silver bullet. And so we can break that down into smaller and more tangible chunks. Here I'm terming them wedges of mitigation effort. And so each one of these wedges represents a technology or activity that can save emissions relative to the pathway or scenario above it. And so each wedge represents a saving of 30 billion tonnes of CO2 over 30 years, scaling from nothing in 2020 up to 2 billion tonnes savings per year in 2050. That's a monumental effort still. These wedges break things down into smaller chunks, but for perspective, the UK's annual emissions are around 400 million tonnes. So to decarbonising the UK completely would contribute just 1/5 of a wedge. These are still enormous chunks of carbon abatement. So the no policy scenario, between the no policy and current policy scenario, we see that current policies are delivering around 17 of these wedges. That's all of the policies that we've stated and enacted today, be it renewable energy targets, be it commitments to reduce deforestation, so on and so forth. Everything that's happened and been stated today is captured in this current policies scenario. 17 wedges. So while it's an admirable effort, we see that there's still a long way to go before we bend that curve down to 1.5 degrees. A further 20 wedges, more than a doubling of existing efforts, is needed to keep us on track for 1.5 degrees. So let's get on to the solutions. Now, there are hundreds, if not thousands, of different climate solutions. Wind and solar come immediately to mind, but there's niche things. For example, making buildings out of wood instead of cement, capturing emissions and burying them underground, simply reducing deforestation. There are lots of different ways in which we can mitigate climate change and reduce emissions, but they can be categorized into 3 broad groups of levers, if you will, that we can pull. The first, and perhaps the most obvious, is technology, right? We've discussed wind and solar, substituting high emission fossil fuel infrastructure and technologies for low carbon alternatives, and in turn displacing the emissions that previously would have arisen. But we also have behavioural change, right? It's not only technologies that we can change our own behaviours. And when amassed across many people, you have real, tangible and material changes in emissions. So an example here would be substituting meat, and particularly beef in our diets, with plant-based alternatives. Lastly, we've got natural solutions, and I've touched on some of those already, but natural solutions encompass everything from deforestation, reducing deforestation, to storing carbon in soils. To qualify as a natural solution, you're storing carbon either in growing biomass or in soils. And so 3 different groups of levers that we can pull. So then, how do we think about which of these levers we should pull? What criteria do we use to decide which of these is better than another one? Because ultimately, we're going to require some combination of different levers, of different strategies. And so the main way of doing this today is using a suite of models called integrated assessment models. Now, these are the bedrock of IPCC reports, and they're very complex and vast, but I will attempt to simplify that down into a very simple overview of what these models do. And so on the left, we see the inputs to the model. Now, this is thousands and thousands of assumptions, but most important of all, economic growth, GDP, and population. These are the 2 fundamental factors that drive our emissions. If we don't produce anything, no GDP, then we don't emit anything. If we don't have anybody inhabiting the Earth, then humans contribute nothing to climate change. These are the 2 fundamental things that drive emissions. And then we've got a whole suite of other assumptions, mostly relating to the competitiveness of different technologies and activities. So you can imagine lots of assumptions about costs, efficiencies, so on and so forth. In the middle, you've got the model itself, made up of interacting modules representing the economy, the energy system, the land system, and the climate system. There's lots and lots of feedbacks, interlinkages, and a huge web of data that is being integrated within that model. At the heart of all of these models is an economic optimization algorithm that tries to tell us what is the least cost way of meeting society's demand for goods and for services. So that's energy services, heating, cooling, cooking, driving. And so all of these different services and goods, of course, you know, the clothes that we wear, the cars that we drive, the building we sit in, all requires something, some energy to produce it, some materials to produce it, and of course leads to some emissions. So yes, all of those goods and services have to be met, and that's what the model tries to do. It tries to meet the demand for those in the least cost way. And what does it produce? What does it tell us? What's the interesting and important information that comes out of this? Well, firstly, it tells us how much it costs to meet that demand for goods and services. It also tells us what the emissions associated with meeting that demand are. Of course, that depends on which technologies the model chooses to deploy. That's characterized by the energy pathway, right? The different combination of things that are deployed to give us to meet that demand for goods and for services. Lastly, land use. It's a fundamental component of the system. We rely on land for everything from food to energy, and so it also provides a land use pathway. So if this model is left unconstrained, we don't limit its behavior in any way, it will have no regard for the climate. It will deploy whatever is the lowest cost technology for meeting that demand, okay? And so often that will be an existing fossil fuel technology that's had decades, centuries of refinement to lower its costs. It's achieved those economies of scale, and it's now much cheaper than many of the alternatives that could come to replace it. But a question that we want to ask these models, and the most common question that we do ask these models, is how can we meet this demand for goods and services whilst also reducing emissions? And to do so, researchers impose a limit on emissions inside of the model that will reflect a different policy goal, right? So we can take that relationship that I showed about cumulative emissions and warming, and then we can say, well, how much carbon could we emit and still stay beneath 1.5 degrees? That then enters the model as an input, a constraint. The model then has to fundamentally change the way it behaves in order to reduce costs whilst also honouring that limit. And so the way that that's typically done is the model raises carbon prices to make low carbon technologies cost competitive with fossil fuel incumbents. And yeah, the carbon price really is the economist's first best solution for that problem, and so it's the general method that the models follow. So the emissions are fixed at the start because we've given it this emissions limit. But prices and GDP and the energy pathway, the land use pathway changes. And these are the useful outputs from the model. They give us an idea, a pathway, a route, a roadmap to how we can reduce emissions at the lowest cost. So just to take it back to the Wedges diagram, so how do these models think we should mitigate climate change, bearing in mind that they're trying to reduce costs? Well, if we take the 20 wedges between current policies and decarbonization, we can look across different modelled scenarios and see what they do. And this is what they do. This is a summary taken from across 367 different models. And looking firstly at the emissions reduction across broad economic sectors. And what we find is that most wedges, shown there on the secondary y-axis, most wedges are achieved in the power sector, so that's electricity generation, and industry, where you've got a bulk of emissions, the largest sources of emissions in the economy, but also a heavy technological focus, right? You've got many technologies that can come in and reduce emissions. Transport contributes a fairly significant portion. Buildings a smaller portion because they're a smaller source of emissions. Notably though, land use, which is responsible for around 1/3 of global emissions, contributes just 1 or 2 wedges, around 1/10 of the overall problem or solution. So then we can zoom in on a particular sector and we can look at and say, hey, well, which technologies are contributing the most wedges within that sector? And so here I've zoomed in on the power sector because it's the largest, it contributes the largest emissions reductions across scenarios. And so we see that wind and solar power, the cornerstones of the energy transition, unsurprisingly contribute the greatest number of wedges. But what is striking about this chart is just how much variation there is across scenarios. Take wind, for example. It can save anywhere between 1.5 and 4.5, nearly 5 wedges of carbon. That's a huge, huge difference. The same applies for solar. What does this tell us? Well, it tells us that the models don't necessarily agree on how we should decarbonize when considering only costs. But costs aren't the only factor that influence preference for different mitigation options, right? And this is a fundamental limitation of these models. This is not to say that the models aren't useful. They've got a noble aim and have a brilliant and scientifically sound methodology for achieving that aim. But humans are not economic optimizers. And least cost is not equal to most likely to be accepted. These are two fundamentally different things. So let's look at an example from an individual. If you saw, or let's suppose you're a wealthy person walking into a car dealership and you're presented with 3 different options. You've got a gas-guzzling sports car that costs hundreds of thousands of dollars, and you've got a very efficient Nissan Leaf EV. Which one are you going to choose? Well, you might not choose the gas guzzler, but plenty of people do, right? People don't always make decisions based on what is cost optimal. You don't walk into a restaurant and order the cheapest dish on the menu. It's one way to ruin a first date. And so, yeah, people don't always optimize based on cost. Governments also don't always optimize based on cost, right? Sometimes governments back solutions that are more costly than others because they confer a geopolitical advantage. Energy security brings that into focus, right? Sometimes governments will pursue an energy solution that's more expensive because it gives them security within their own borders. Take the UK, for example. For some years, onshore wind has been the cheapest way of generating electricity in the UK, but it faced a de facto ban for almost a decade because people didn't want to see these wind turbines pop up in their garden. And so that's something that can't be encoded easily into a cost-optimizing algorithm. People and governments don't always think long-term. Party political cycles dictate how governments respond to different pressures in society. And people and governments are unpredictable. They do strange things. Take the wavering support for, or the wavering involvement of the US government in the Paris Agreement, for example. In, out, shake it all about. I take the UK government at the last election, for example, the turn on net zero. We're going to remove the ban on internal combustion engines or push it back, so on and so forth. Governments change, people change, and these things aren't captured well inside scenarios. People often make myopic decisions. And so, lastly, and perhaps more fundamentally, projecting future costs is inherently uncertain. How much is a solar panel going to cost in 2040? We could all have a guess, and we could pull some experts together, and we could look at past, the learning curve, the past cost reductions in solar panels, but we're never going to know for sure. And the problem is that if one, or indeed many of these assumptions are falsifiable, so too is the pathway that has been built around them. Again, this is not to say that these models aren't useful, but it is to say that they can't be the only tool we use for reasoning pathways to mitigating climate change. So then what's missing? Well, all of the non-economic factors that shape preference, vested interests, convenience, security, so on and so forth. There are lots and lots of different factors that influence the decisions we make. It's not always cost, and will never always be cost. Because of the economic framework within which these models operate, behavioural and natural solutions that draw value in different ways are often neglected. And so they're underrepresented in scenarios, and their potential is perhaps underestimated. Lastly, equity and justice considerations. Consider that universal global carbon price. That's quite regressive. And the consequences of that for the poorest and most vulnerable communities, that's not being considered by the model. And so, yeah, the models have many limitations. They are very useful, and they have produced lots of useful pathways, but again, they can't be the only source of information we rely upon. The final limitation is one of, it's difficult to move past. As I've shown in the previous slide, we've got hundreds, thousands of pathways, and they come to different conclusions. When you're presented with this sprawl of scenarios, how are you supposed to know which of these, which all profess to reduce emissions at the lowest cost, is right? You can invalidate any and all of those scenarios. And so, yeah, we need a different way of building consensus around which strategies we should be deploying to mitigate climate change. So we've got another poll here. So this question is taken from the UN's People's Climate Vote, where they survey people around the world and ask them a few simple questions about how they would choose, or how their country should choose to mitigate climate change. So one of them, how quickly should we swap fossil fuels for renewables? Okay, so we're tending towards very quickly or somewhat quickly. That kind of reflects the balance that we saw in that first poll, right? Most people 1.5 or below 2 degrees, and you would expect in those pathways that we need to reduce fossil fuel consumption either very quickly or somewhat quickly. So yeah, those not at all or don't know, fair enough. So yeah, how does that compare then to the global picture? It's broadly similar. Most people around the world think that we should transition away from fossil fuels very quickly or somewhat quickly. There's a not insignificant portion of people that don't think we should. I mean, 1/4 of people think we should transition slowly or not at all. So people have different perspectives on how we should go about mitigating climate change, or indeed whether we should mitigate climate change at all. And these vary regionally, right, and in ways that we can't predict. And so if we look at a country example here of Nigeria, you've got really strong support for the transition away from fossil fuels. We can contrast that against Morocco, where you've got a completely different picture, much slower transition being supported there. So we'll take one more question out of the UN's climate vote, and this is how much should we protect and restore nature in order to mitigate climate change? So we're seeing much greater consensus on this one. I think everybody in this room, and I should hope, except for a few people, everyone in this room, I should hope, would wish to protect and restore nature, whether it's for climate change mitigation or just for the general health of the planet and us. So yeah, we see much broader support for protecting and restoring nature. And again, that's what we see around the globe. Yeah, so let's take it a little bit deeper now. I've asked two broad questions that encapsulate lots and lots of different technologies and solutions. We can reduce fossil fuel consumption in myriad ways, and we can protect and restore nature, again, in multiple different ways. So let's take it back to the wedges. We need 20 wedges to get from current policies down to that decarbonisation scenario. Let's have a think about how we should and could do that. So I'm now going to walk through a whole host of different strategies that can each achieve a wedge. This is kind of Climate Solutions 101. And so we've got every single strategy that could feasibly achieve a wedge, that 2 billion tonne saving by 2050. And then I've gone away and calculated how widely we'd have to deploy each of them to get a wedge. So just a quick explanation. So here's two potential wedges from building solar farms and building more wind farms. The little red icons show us how many wedges could potentially be achieved in total. So wind and solar, there's lots of fossil fuel power generation. We could therefore achieve lots of wedges from deploying wind and solar power. And then the little sentence that lives beneath it is telling you how wide we must do this thing in 2050, or how widely we must adopt this thing in 2050 in order to achieve one wedge. And so for solar and wind farms, we need to generate around 7% of global electricity to achieve a wedge. The same applies for nuclear reactors, as they're also a zero carbon source of electricity. We could switch from coal power plants to gas power plants, which produce roughly half the carbon emissions per unit of electricity. Or we could retrofit coal and gas-fired power plants with carbon capture and storage technology to capture that CO2 and then bury it underground. These require a different amount of different levels of deployment because although gas has lower emissions, retrofitting CCS to a coal power plant saves more emissions because coal has more emissions to be saved. We can also use a technology called bioenergy carbon capture and storage, which has grown to prominence in recent years for its potential to remove CO2 from the atmosphere. We grow trees, which store CO2. We then burn them in a power station and pump that CO2 underground, creating a so-called negative emissions loop. We have, there's lots of different trade-offs and synergies and factors that will affect people's preference for different technologies, right? Of course, we have costs. So let's think about the costs of these different things. We have wind and solar farms, which are the cheapest source of electricity generation across much of the world today. But they also require lots of land. And in the case of both wind and solar, they require lots of critical minerals. Switching from coal to gas might be perceived as an easier solution because we've already got lots of the infrastructure in place, but it also leaves behind residual emissions. You're only reducing half the emissions from the coal plants. Just to each of these technologies, carbon capture and storage is never going to be as cheap as unabated coal or gas power plants, right? Because there's an additional energy cost and a cost associated with storing the CO2. but they slip more easily into the energy system because they have the same properties as a normal gas, an unabated gas or coal-fired power station. Unlike wind and solar, they're not variable, subject to the wills and wants of the weather. Bioenergy carbon capture storage, we can see the trade-offs there. It's potentially provides this negative emissions loop, but at the same time it competes for land and water with food and commodity agriculture, which is already stretched today. So lots of different trade-offs, lots of different synergies, benefits, and costs. So moving over to industry, we could produce clean hydrogen and use it in various different ways. We could use that clean hydrogen in the petrochemicals industry. We could use it to produce fertilizers, reducing emissions from the dirty hydrogen that we produce today. We can build direct air capture. It's the ultimate end-of-pipe solution. It's like a giant carbon vacuum cleaner that sucks CO2 out of the atmosphere using chemical sorbents and electricity. But doing so would be an immense undertaking. To achieve a wedge, we would need to deploy 500,000 of the world's largest direct air capture facility. Out to 2050, that's roughly 50 plants per day. We could decarbonize steel and cement using CCS, or in the case of steel, we can also use some clean hydrogen. With cement, you have to capture the emissions from almost all of the plants, and for steel, use a combination of hydrogen and CCS across 40% of plants to achieve a wedge. Lastly, we can reduce emissions of quite potent greenhouse gases throughout different industrial supply chains. So we can reduce methane emissions from oil and gas supply chains that are leaked and vented throughout the upstream and downstream activities. And so reducing those by roughly half would give us a wedge. And we could reduce refrigerant emissions. So this is less known compared to other solutions, but refrigerants contain very potent greenhouse gas emissions, hydrofluorocarbons, which on per unit of gas have a warming impact 1,200 times that of CO2. So a small and more concentrated source, if we can stop that, or reduce it by 2/3, then we can get a wedge too. Again, lots of different trade-offs between these. Hydrogen is potentially expensive but versatile. Direct air capture offers no real benefit to society but could be justified if it's cheaper than other solutions or if we're just that resistant to mitigating in other ways. CCS has had a really long and hard battle with scaling, right? We've been looking into this technology, lots of R&D and investment for decades and still hasn't managed to take off. Doesn't mean that it won't in the future, but it faces different challenges. They're reducing refrigerant and oil and gas methane emissions. They're more diffuse sources, right? You've got to look across this entire system. You've got to be recycling and destroying refrigerant emissions across many different devices. Ultimately, you have to have industry's cooperation in order for those to move forward. But they can achieve emissions reductions at lower costs. Reducing methane emissions in oil and gas, roughly 3/4 of those could be paid for themselves just by capturing and then reselling the gas that was formerly emitted. So different pros and cons. So I want you to weigh those up now and think which of those strategies, which 6, would you choose if you were constructing your own decarbonisation pathway? There's a pretty even distribution across options there. Solar power emerging as a potential winner. Carbon capture and storage relatively popular. Hydrogen also has its backers. I'll give you another minute or two to punch in your responses. Okay, so yeah, we see that people have fundamentally different preferences for different solutions. Wind and solar emerge as clear winners, probably because they're already decarbonising electricity generation the world over today. But yeah, lots of different opinions, lots of different feelings, presumably based on different preferences, values, beliefs. There we go. Okay, and so now let's move on to transport and buildings. So here we've got lots of solutions in transport that decarbonise personal transport, right? It contributes roughly half of global transport emissions. So we can deploy electric vehicles, or we can use more biofuels in the transport sector. Alternatively, we can improve the efficiency of internal combustion engine cars. Reducing their fuel use by 50% gives us a wedge too. It's not just personal transport. Reducing emissions from freight transport by about a third contributes a wedge also. We can avoid travel or walk or cycle. You know, avoiding travel could be teleconferencing instead of commuting to work. We could also use more public transport. A controversial one, but flying less can also deliver a wedge, but it requires a whopping 70% reduction, grounding 70% of flights the world over in order to give us a wedge. For perspective, that's about the same reduction we saw at the height of the COVID lockdown. In the building sector, we can install more heat pumps, delivering roughly 2/5 of global heating. We can deploy clean cook stoves, replacing 75% of the inefficient cook stoves that are used largely across the global south with clean alternatives. A bit of a win-win there because you're reducing indoor air pollution and all of the harmful consequences of that at the same time. Lastly, a bit like the car efficiency wedge, you can improve the efficiency of buildings, reducing the amount of heat transfer by insulating buildings by around 50%, also delivers a wedge. Again, we've got this intricate web of trade-offs and synergies and different costs and a million different criteria with which you can appraise each of these strategies. Electric vehicles are already scaling. They're a proven solution, right? 1 in 4 vehicles sold today is electric. And so they might seem like an obvious solution, but other people will disagree. They've got heavy critical minerals requirements, which of course have ramifications for societies that are built around extracting those critical minerals. Biofuels, oh, okay, that's easy. We can just drop in a clean fuel. But again, they're competing with food and commodity agriculture. For land, we could take, public transport or active travel, but these solutions are going to be more applicable to some places than others. If you live in a sprawling city with no sidewalks, that's going to be a really tricky solution to implement. The same goes for buildings. Heat pumps have quite a high upfront cost. They might be able to save us some cash over the longer run with reduced operating costs, but you've got to convince people to put up the money upfront. And so, again, a huge number of criteria of which we can appraise these options. And I'm going to leave it up to you, again, to look and to tell me which of these options you prefer. Okay, yeah, so again, we've got quite a spread there. Public transport winning with insulation just behind. It sounds like a horse race now. And then electric vehicles coming up from the back. Again, lots of different preferences for different options. And this is in a room of people that have presumably more similar ideologies and environmental beliefs than others. So yeah, I've made a note of generally which of those are most favoured. So let's skip over in the interest of time now. So then lastly, this is an energy transitions lecture, but I could not finish without looking at the land sector and food production, where there are many other strategies. So I'll go through these a bit more quickly. But you've got reducing tropical forest loss. If we reduce that rate by roughly 2/5, we've got a wedge. Re-wetting tropical peatlands, if we re-wet all of those and stop any further drainage, we can also get a wedge. Expanding tropical forests by 7% or temperate forests by 1/4 gives us a wedge as well. We can have multi-land use settings, so we can grow trees inside of existing agricultural land, inside pastures and inside croplands. We can apply soil carbon management, so that's reducing the extent to which we plough soils, planting cover crops to stop soil organic carbon from oxidizing and turning into carbon dioxide. A slightly off-the-wall solution, we have enhanced weathering, where we can apply weathering materials to croplands, which effectively store CO2 from the atmosphere, and then it dissolves outside of the materials and is flushed to the oceans. But again, it's a kind of carbon removal technology. Lastly, we've got a couple of behavioural solutions. We could reduce food loss and waste by half, or we could reduce meat consumption in the regions which overconsume by 1/3. The regions that overconsume are basically everywhere outside of sub-Saharan Africa and South Asia. And so a whole host of land and food-related strategies, which are often foregone by the integrated assessment models. And so I'll ask you again quickly if you could just pick your top 5 strategies from that menu. Okay, so we've got reducing deforestation, looking very popular. Also reducing food loss and waste and meat consumption. Reforestation has some backers as well, and managing soils too. And so in the interest of time, I'll move on. We can punch this in to a website that myself and a colleague have built, which is the Climate Wedges website. And we can construct our own decarbonisation pathway. We did that solar. That was a very popular strategy, so we can punch in 2 wedges. We had wind farms, nuclear hydrogen, so nuclear. And then in industry, we had hydrogen, we had cement, we had reduce oil and gas, EVs, we also opted for active travel, public transport, cook stoves, which are in buildings, heat pumps and insulation, and then this was a big favourite, so we'll really reduce tropical forest loss, reforestation in both the tropics and temperate, reducing meat consumption and reducing food loss and waste are, of course, the soil carbon management. And like that, sorry for the clunky interchange there, we've built our collective decarbonisation pathway. We've got some solar in there, some wind, nuclear, hydrogen, cement, methane emissions reduction, so on and so forth. And you can see how adding each of these different mitigation strategies acts to reduce emissions. So here we've gone from that current policies pathway all the way down to the 1.5 degree pathway. Okay, so with that pathway in mind, we've come to an almost consensus decision. I would then ask you, hopefully this is going to load, to tell me how satisfied you are with that resulting pathway. Has compromise led to a healthy consensus, or has it led to a pathway that nobody likes? Okay, I'd say, based on the responses that have come in so far, we've done a pretty good job of finding some consensus and a happy medium. Most people are very satisfied or somewhat satisfied. There's a fair few who are indifferent. So let me just move forward one more slide. So then I will ask you, as you sat there with your phone and selected between different options, what were the main factors that drove your decisions? Was it cost? Was it convenience? Was it security or geopolitical considerations? What factors drove your decisions? Okay, so feasibility, effectiveness, ethical considerations coming up a lot there. Urgency, equity, realistic options, things that you can do yourself. There's a whole host of different things springing around that board now. I can't even see. Cost is just a tiny little word inside this much broader cloud there. And so what does this tell me? It's, again, that people just have fundamentally different preferences for options, but also how they've come to those decisions, why they've chosen the pathway that they want. And it also tells me, that we need a different approach, a change of tact in how we think about decarbonisation pathways. Because ultimately, we need to bring everybody along. We need almost ubiquitous societal buy-in for these pathways to be realised. You can't tell people that this is going to cost less money and expect everybody to go for it. Ooh. So finally, again, sorry for running a little bit over here, but some final reflections. So individuals like you or I are actors who contribute to climate change, need to deal with its impacts, and then identify, develop, support, and implement climate solutions. And so involving them is not an option, but an absolute imperative. And what have we learned? Well, we need a mix of strategies. There's no silver bullet. Taking into account all the different constraints on strategies, how many wedges each strategy could achieve, getting that 20 wedge combination needed for 1.5 degrees, that could be achieved in 6 trillion different ways. So there is an insane array of potential decarbonisation pathways out there. Looking at cost alone and having the integrated assessment models help us decide has helped to narrow that possibility space, but it's still enormously wide. And so we need to narrow it further around the options that are most acceptable and not necessarily those that are least cost. Unless we bring everybody along, the transition is not going to happen. Where does this start? Well, we need to better understand people's preferences. I feel like I've got a slightly better idea of your preferences after this session, but ultimately, all of this starts with dialogue, informed by frameworks like the Wedges, being able to trade off options on similar terms inside of a common language. Lastly, or ultimately, the collective power of individuals should not be underestimated. We look at those behavioural strategies. Building up from an individual to a population can leverage huge impacts. We need people to shape politics, corporate decisions, and society at large. And lastly, we should think of the benefits of the transition as well as the costs. We need a new framing. We can build cities with clean air, with rapid transport, 15-minute cities. We can have regenerative agricultural systems that deliver products with tangible health benefits. Reducing meat consumption is not only a win for the climate, it's also a win for people's health. So there are lots of win-wins to be had, and the transition can bring jobs, it can bring all sorts, but too often we focus on what it's going to cost. And so lastly, I'll leave you with this image, which is, which world do you want to live in? The one on the left or the one on the right? Okay, thank you.